Welcome to this second lecture of the short course on machine learning in communications. As you may remember, in the previous lecture, we covered some basics of machine learning to make sure all the attendees are on the same page. Now, this lecture onwards, we are going to discuss the role of machine learning in communications. This is a bit of an introductory lecture in that sense. So we are in this specific lecture, we are going to cover three main things. We will start with a simple signal detection example to reinforce the importance of choice of appropriate loss function and performance measure. So these ideas were introduced in the previous lecture, so I just wanted to reinforce them. Ideally, I wanted to cover this example in the previous lecture itself, but we were just out of time, so I'll cover it here since it is also related to communications. Then we will discuss some potential classes of communication problems that will benefit from the application of machine learning. I just have a brief discussion on what type of problems would benefit from the application of machine learning, and also provide pointers to future lectures where we are going to discuss some of those problems in more detail. Okay, then we will conclude this with a case study on determinantal learning for wireless networks. Okay, so we'll talk about that in more detail. So we are using the idea of supervised learning in this case study that we have already introduced in the previous lecture. So let's first begin with this simple binary classification example, which has connections to signal detection as well. Yeah, and in order to convey those two ideas that I mentioned in the previous slide, I will be assuming that your data set is unbalanced. Okay, what do I mean by that? Let's see. So we are going to assume that you have a data set in which each point, right, has a binary label. Think of your received signal where binary label corresponds to whether your transmit signal or your target, right, whatever you might be detecting, is that was that present or not, right? So are you receiving an actual signal or is it just noise, right? That would be binary label. Assume further that one of the labels occurs very infrequently. This could be a case where, say, a signal detection problem in which the message is transmitted very infrequently, right? So most of the time you are receiving just noise, but every now and then you might have a message, right? So the transmission of message is very infrequent. Now, in many such problems, it is actually detrimental, more detrimental if we miss a signal, right? Just because your signal is so infrequent, right? We should not be missing it. Then if we detect a signal that was not there. In other words, false negatives are more critical than false positives, right? So false negative means, right? False negative means you had a signal and you missed it. False positive means that you didn't have a signal and you detected that you had a signal, right? So it's a false positive in that sense. So we are saying that in many of these applications, false negatives are more critical. So we should try to avoid them as much as we can. And there is actually a nice analogy of this setting with a medical data set, right? Assume that we have binary labels in say patient data set corresponding to patient data, which signifies whether a given patient has a disease or not, right? So here your attributes could be, so they are attributes for the patients, which could be age, where they live, their say diet and things like that. And then you have a binary label, which is whether that patient has a disease or not, right? Now, it is really, really critical to detect correctly when a patient has had this disease, right? Otherwise, the treatment might get delayed. Now, on the other hand, of course, it is bad, right, to misclassify a healthy person having, as having that disease, but it is, say a relatively easy problem to fix because you can run more tests to be sure, right? Now, if you look at the choice of a loss function in this case, right? So we introduced 0-1 loss in the introductory lecture. In this case, it is clear that we should not be choosing a 0-1 loss, right? So the loss, we have loss associated with a false negative is actually much higher than the loss associated with the false positive. So we should be careful in how we construct the loss functions. And moreover, we should also be very careful in how we measure accuracy in these type of cases, especially with unbalanced data sets and so on. And as we will see, this is something which we have been studying in some context in communications as well. Now consider a data set, same example, consider a data set in which only 0.1% of patients have a disease, right? Very infrequent occurrence of a disease, 0.1%. Where rest are healthy. Now, of course, you can think of this equivalently in terms of a signal detection problem as well, right? Now, let's say that you learned machine learning recently and proposed an algorithm that gives a 99.5% accuracy, right? So 99.5% accuracy, which is pretty good. And accuracy we are defining as the percentage of points that were correctly classified, right? So you're making mistakes only 0.5% of the time. And you reasonably ask, is this a good algorithm, right? And in order to answer that, let's consider another trivial algorithm. Let's consider a trivial algorithm in which what I do is I just, irrespective of my input, I just assume y hat equal to 0, right? I just say that, irrespective of the input, that this person doesn't have a disease, right? In this case, if you look at the accuracy, it is actually 99.9% accurate because only in your data set, only 0.1% of the data points were corresponding to the diseased individuals, right? So then the obvious question to ask is, why is this performing better than the algorithm that you designed, right? And the takeaway is that we need to be very careful in how we measure accuracy, right? So your algorithm might actually be doing better, right, on the data points that matter. But it's just that since we are looking at a very naive measure of accuracy, we are not able to capture that. Okay? And that is captured, interestingly, using the idea of a receiver operating characteristic curve. Okay, let me discuss this in detail. What exactly is this this ROC curve? So we pronounce this as ROC. On the x-axis, we have a false positive rate FP. On the y-axis, we have a true positive rate TP. Okay, and we are claiming that any practical classifier, let's say any practical binary classifier that you will develop, will have this type of a curve. This type of we call it a ROC curve. Right? One can easily argue that if you just flip a fair coin, this is where you will be operating, right? Your false positives and the true positives. And if you had a ideal classifier, more like a Gini case, right? Then this is the point that you should be striving to operate at. False positive 0, true positive so on, right? Of course, that is not practical. But in practice, you will be operating somewhere in between this just flipping a coin and the ideal classifier. Okay. You can actually think of this curve, ROC curve, corresponding to a practical classifier in terms of signal detection. Okay. Now, for that, remember the dependence of the true positive and false positive rates in the signal detection problem on the signal detection threshold, right? You are detecting a signal by comparing some metric that you come up with, right? It could be the signal energy, and you compare that with some threshold, right? So if I set that threshold extremely high, right? Let's say so let's say I choose that threshold to be, say, 1 million, right? And your signal power is very small. So in that case, I'm just not going to detect any signal, right? And that is what will correspond to this point here. Very large value of a of your detection threshold. Now, on the other hand, let's say I choose very small value of the detection threshold. This is the point that will correspond to, right? Your false positives will be 1, your true positives will be 1. You're always detecting a signal just because your threshold value is so small. And as you change from a small to a large value, right, you basically scan this whole curve corresponding to the practical classifier, right? So each point on this curve corresponds to a different signal detection threshold. Okay. And the interesting thing to note is that we use this curve in communications, right, for many years. For example, people working in radar would have seen this many, many times. And it turns out that this ROC curve, along with another similar idea, which is precision recall curve, it is one of the standard tools used in machine learning to characterize the performance of classifiers, right? So, of course, we will be using ML in COM, but we have found an example where something that has been classically sort of studied in communications has also impacted classically the machine learning literature as well, right? And it doesn't really, it wouldn't really surprise you, right? As we proceed in this course, there are some very interesting connections in these areas. Okay. So before we move forward, right, I just want to introduce artificial neural network. What exactly it is at a very high level. If we get time, I will go over this in a lot more detail. But in communications examples, if I say a neural network, or we are say training a network, or we are finding the function approximation and things like that, right, that should intuitively make sense to you. And in order to do that, I'm just giving a very quick, like 2-minute preview of what a neural network is. What exactly does it do? Okay. So artificial neural network is composed of multiple artificial neurons, and a neuron, one way of modeling at least a neuron is as follows. Okay, so you have inputs to this neuron. Right, and these inputs could be your features. Let's say your feature x1, x2, x3, so on up to xd. And then you oftentimes also have a bias term, which is considered to be 1. Okay, so you then calculate what we call an activation function. A is I equals to, say, 0, because you have a bias term, t. Beta I xi, where as was the case before, betas are just the weights. Beta 0, beta 1, beta 2, beta 3, beta d. Okay. So then what you do is you compute a response, right, on this value a, which is defined as some, say, y hat, g of a. And this is a response function. And it is often nonlinear, right? It will be nonlinear. And we are going to look at some examples of this when we study, for example, logistic regression. So now the way you stack this artificial neuron into a neural network is the following. Let me add a page here. Is the following. So you have these input features, x0, which is your bias feature. Then you have x1, x2, so on up to xd. Right? These are given as inputs to your first so-called hidden layer of neurons. Okay, so what do we mean by a hidden layer of neuron? So you have this neuron, let's say A1, A2, so on up to A, let's say some AM, right? The number of neurons you have in the hidden layer or layers doesn't necessarily have to be equal to the number of features that you have. And there will, of course, be again a bias term. Let's say bias term is just a 1. And then what you do is, let's say it's a fully connected network, right? We won't be going into the details of what do we mean by fully connected and what are the implications rather of fully connected and so on. Fully connected just means that all the inputs go into right? All the features are connected to all the neurons, and then the same thing repeats in the other layers as well. Okay, so you have this here, this here, this here, this here, right? So now you can think of this as a single neuron, right, on which this to which you're giving this input, and then the same thing happens here, right? So this goes here, this goes here, this goes here, right? So did I connect everything? Yeah. So this will come here, this is gone here, and this will come here. Right, so fully connected, all the inputs are connected to all the neurons. Now, each of these neurons will compute a response function, right, nonlinear response function on this activation, right, on AAM. So let's say that those responses are, say, H1, H2, and so on. Right? So this will go as an input to another neuron, A out, right, whose output we will be observing, let's say y hat, which is g of A out, which is g sum I equals to 1 to m, some weights, right, beta oi, hi. Okay, so these HMs again are the outputs of the neurons. They are not the weights. The weights will remain beta i's, right? And of course, your bias term is connected here as well. As I said, again, this is very, very quick overview because I just want to convey what the general idea is and then just move on and not go into the algorithmic details because that will just take a lot of time. Okay, so here we have an input layer. Input layer, you have a hidden layer, and you have a output layer. Right? Hidden layer meaning you're not basically observing that, right? You're observing only the output and you know what the inputs are. So whatever is in between is hidden from you. Okay, so what matters to us, right? So this structure, right, or again, for the purpose of this course, that's not really what is important to us. What is important to us is what can a neural network do? And its most important function is the universal function approximator. It is known that a neural network with only one hidden layer, right, and with linear outputs can uniformly approximate any continuous function to arbitrary accuracy, right? Given you have enough hidden units, so you need to have many. You may need many neurons, right? It has been shown, of course, in many applications, and then depending upon the structure of your neural network, right? If you have a large structure, which means the hypothesis class that we introduced already before will be large. So you are learning a large hypothesis class, you might need more data and things like that, right? Another thing, which again, depending upon if you have been exposed to machine learning or not, is the fact that neural network can do feature extraction for you. So you don't really need to create features. It can do that implicitly during the training process, right? Again, if this did not make sense to you, you can completely ignore that. It's not going to impact what we are going to study next, right? So I just wanted to get this out of the way. What exactly is a neural network? How does it work, and so on? But if I have to introduce this more formally, I probably need like maybe at least 1 hour, or probably both hours on a given day to introduce this, and then introduce the algorithms needed to train it and study the implications and so on. Okay? And for the way I'm structuring this course, we don't really need that information, right? So you can read one of the textbooks that I referred in the previous lecture, and most of them has this information. So you should be able to find that quite easily. Okay. So with that very quick note, let's move on to what matters to us, right? Which is the communication problems that can benefit from ML, right? Let's just get to the main ideas quickly. Now, remember from the first lecture that a machine learning problem will be meaningful if you have some pattern to learn, you have data to learn that pattern from, and it should not be possible to describe that pattern mathematically, right? If it is possible to describe your pattern mathematically, as we'll be seeing in the very next slide, you can obviously do much better than what ML would do, right? Given this, there are, say, and again, this is not an exhaustive list, but say 3 classes of problems that will benefit the most from machine learning. Okay, and I have designed case studies for each of them. The first one is some algorithms may be prohibitively complex for real-time implementation, right? So you have an algorithm, just because maybe your network size is very large, as we'll see in our case study today. So in those type of cases, machine learning can really help with coming up with real-time implementation, or in general, just more efficient implementation. Second class of problems where machine learning can be very helpful is when your mathematical models are either inadequate or incomplete to describe the data, right? And we'll look at one problem on, or one case study rather, on day 3, where we will have some data on a Grassmannian manifold, and just describing that data will be difficult. So we come up with a machine learning based solution for that case. Number 3 is data-driven applications, right? So applications such as edge learning, which are just inherently data-driven. So this will be a case study on day 4 when we will be looking at distributed learning. Okay. So you can see from here that this lecture is just the start, right? When we start discussing the role of ML, but this theme is just going to continue on all 4 days. Okay, so before we discuss where machine learning makes sense, let's actually first discuss in which type of problems ML does not make sense, right? Let's just get that out of the way through a very simple example that I came across recently. So this example is a QPSK example that I found in IEEE Signal Processing magazine, a recent paper by Emil Johnson. So the problem is as follows. You have a QPSK signal. As you know, in QPSK, we have 4 constellation points, right? Each point mapping to bits. For example, you have this point, this corresponds bit 0, 0. This point corresponds to bit 1, 0, and so on and so forth. Now you transmit a signal, right, and use a AWGN channel. Your received signal is obviously not going to correspond to this constellation point. It may be close because you have Gaussian noise, but it is not going to be exactly that same point that you transmitted. So what you eventually get is sort of cloud of points around each of these constellation points, right? So what the authors did, and before we go into the ML solution, I think most of you would have recognized that this is, of course, a very, very well-studied problem, right? If you are using QPSK and you're detecting this signal at the receiver. So we do have a maximum likelihood solution for this. But then these authors were wondering, if you apply deep learning, if you use a neural network, right, using this data, what would that neural network give? So let's look at that solution very briefly. Okay, so here I'm showing 2 pictures. This right picture is the maximum likelihood solution, very well known. And one thing I wanted to highlight is that this is the square that I showed you in the previous slide, right? So this is sort of a zoomed out version because they wanted to see how ML was generalizing in the region. Machine learning was generalizing in the region where the samples were not seen, right? If you remember, most of the samples were concentrated here. Okay. So first of all, this right picture, this should make a lot of sense to everybody, right? So you have these detection boundaries. So if your received signal lies in this quadrant, right, then you will be mapping that to this constellation point, right? Simple ML detection. On the left is what you get from a neural network, right? I would say it's doing, something reasonable. But it's not giving you exactly the solution that you are looking for, right? So there could be many reasons. There could be overfitting, as we discussed before, and overfitting is actually one of the key problems with neural networks, just because the architecture could be very complicated. So it all depends on what type of architecture you chose. But the point the authors and I guess me as well, we are trying to make here is you should just not apply machine learning if you can do something which is more concrete, more rigorous, right? Now, of course, this problem could change just by changing your noise model, If your noise model is something for which you cannot design a receiver directly, then sure, a machine learning solution in that case could help, right? So machine learning will give you a heuristic, basically a heuristic solution, right? So with most of the times with no performance guarantees, right? So that should always be kept in mind, especially in this discussion of whether we need communication information theory fundamentals or not. Right? So can machine learning solve all the problems? Okay, so let's start our case study for today. And this case study is determinantal learning for wireless networks. Okay, we will see that this is one of the settings where machine learning actually solves a problem which cannot otherwise be solved, right? It just becomes prohibitively complex. So it's not that we are applying ML to a problem for which a nice, efficient solution exists, right? And this setting is interesting in its own right, because we'll be using ideas from two different areas. We'll be using ideas from, obviously, from machine learning and also from stochastic geometry. So for those of you, I'm sure most of you here would be familiar with what stochastic geometry is. It's the study of point patterns, right? Study of random shapes and patterns. And it has been applied extensively to the study of wireless networks, where wireless nodes have been modeled as random point patterns, as I'll show next. And then ideas from stochastic geometry have been used to analytically characterize their performance, right? So me and my students have written a few papers in this area, and one paper is on this connection of stochastic geometry with machine learning. And this case study is based on that paper, which I'm quoting at the end of this slide. So this was led by my graduate student, Chiranjeev Saha, who is with Qualcomm now. So I would like to thank Chiranjeev for his great work in this paper. Okay, so, based on what I just said, right, you might feel that stochastic geometry and ML may not have anything in common, right? So where exactly is the connection? So the connection comes from, at least one connection comes from the way determinantal point process, which is a specific object in stochastic geometry, the way it has been used in both machine learning and stochastic geometry communities. Okay, so let me first explain what at a high level what a determinantal point process is, right? So you might have heard about a Poisson point process, and those of you who have not been exposed to stochastic geometry but might have come across things like queuing theory, right? You might have come across Poisson arrival processes and so on, right? So in those type of models, your points are placed independently of each other. They can come arbitrarily close to each other, right? But then there are other point process models in which you can introduce either attraction or repulsion based on the application that you are studying. And in this application, we actually want to introduce some type of repulsion in the point so that the probability that 2 points lie very close is very small, right? So that's really what determinantal point process does. And the way it has been used is to model locations of macro base stations in a cellular network, right? We know that your base stations will not be deployed very close to each other, right? In most realistic deployments. So a determinantal point process has been used to describe those deployments. So this is a picture from one of the papers we wrote back in 2015 with the Yingze, Francois, and Jeff Andrews. On the use of determinantal point process in wireless networks. So here I'm just showing this is the base station data from the city of Houston, and these are so the thought process here is to think of this data set as a realization of a determinantal point process, then fit a determinantal point process to this data set, right? I won't be going into the fitting details. And then create another realization of DPP and see if it looks similar to the Houston data set or not. right? So this is what you get after when you use a Gauss DPP and likewise Cauchy and generalized gamma DPP. So different models of DPP, and just through eyeball rolling, you can see that we are sort of capturing the characteristics of the data set. And at a very high level, this is the thought process we'll be using later as well, right? You have something deterministic, and you treat that as a realization of a point process, and you use DPP to sort of model that. And another point here, which is a little bit intriguing, is if you think about this data set, right? This is a result of many different types of optimization, right? You don't place a base station randomly at any place. There are many types of restrictions, including, site acquisition restrictions. Then you are doing a lot of frequency planning and things like that. And then your base stations are placed. And it turns out that once you treat that as a data set, you can actually describe that as a point process. So that's something that I found quite fascinating. Now, on the machine learning side, as will be clear throughout this example that I'm presenting, DPP has been used as a probability model for subset selection. Okay, so this idea will be clear from a recommender system example that I'll give. All right, so let's start with discrete point processes. Let's just try to see how to define a discrete point process. So in order to define a discrete point process, we have a ground set which contains n items. So that ground set is denoted by y. So this is your ground set. Then you can define a power set, right? And each element in this power set, which basically corresponds to each subset of your ground set, right? You can put a probability measure on that. And that's how you define discrete point processes. For example, in this subset, right, I can put the probability of occurrence of this subset to be 0.02. I could put the probability of occurrence of this subset, right, as 0.01. So you have a base set from which you are selecting. And this setup will be quite essential for the type of application we'll be studying. Just to make ideas concrete and also to introduce the notation, if you have an independent point process, which means that the probability of selection of a given point is pi independent of the others, then you can define probability of a given subset, py, as just the product of pi's corresponding to the points that are lying in this subset y times the probability of 1 minus pi, right, of the points which are not included in the subset. Okay, so now let's introduce what a determinantal point process is. DPPs are probabilistic models that quantify the likelihood of selecting a subset, right? So we are putting a measure on a subset, and that measure is defined as the determinant of a kernel matrix. Right? So all that is not really necessary, but let me just go through the details for those of you who are interested. So you have kernel matrix K, which will be describing this probability. So we have two different definitions for DPP. Definition one, you can think roughly in terms of the CDF, and definition two, sort of in terms of PMF. So definition one is what we call a K matrix formulation. So here you have a ground set of n items, as we said in the previous slide. This ground set is Y. Now, DPP is a probability measure on the power set 2 raised to power y, right? So it gives you the probability of selecting a specific subset of this ground set. Now, a random subset y, think of this y as a random variable if you're trying to create an analogy with the random variables. It follows a DPP if probability that any subset A, right, lies in this random subset y, right? So think of this as probability little x smaller than equal to the random variable x, right? This is equal to determinant of Ka, where Ka is defined from your kernel matrix, right? So let's say that A is only, say 1, 2, right? And you have a large kernel matrix. So in that case, you will be defining Ka by just using the first row, first column, right? So these all the elements that are contained in the A. First two rows, first two columns. Okay. Now, K is a positive semi-definite. It can be shown that K is positive semi-definite, and you can also show that the eigenvalues of K are upper bounded by 1. There is another definition which is actually a little bit more useful for us, which is sort of the equivalent of a PMF. It can be defined now, your PMF can be defined in terms of a matrix L, right, which is again whose eigenvalues are upper bounded by 1, and you can also sort of index that in the same way as we did K. In this case, you can directly define the atomic probability of a given subset, occurrence of a given subset, as PLY. This is nothing but probability that your random subset is equal to a given subset, right? So the atomic probability of that, you can define that in terms of determinant of Ly. Okay. And then there are some additional details like, how is K and L related and so on. So we discussed all that in the paper in case you are interested. But here I want to make sure we sort of focus on the bigger picture idea first. All right, so now let's study this ability of DPP, right, to introduce this quality diversity trade-off, right? And this is also the reason why we are so interested in using DPP for the case study that we have in mind. We want this quality diversity trade-off in our subset selection. Right, so at a high level, the way you introduce this quality diversity trade-off is by defining your matrix L. So here you have Lij, which is the ijth element of L, in terms of some quality and similarity terms. Okay, so here you have this first term, which gives you the quality of the ith item. You have the second term here, which gives you the quality of the jth item. And you have this middle term here, which tells you how similar those two items are. Okay, without going into exactly what each notation means. So you can also now write the probability PL y equals to y, which is the atomic probability. You can write this now as determinant of SY, determinant of the similarity term, and the product of these quality terms, right? Although not very important, it also has this graphical representation where you can think of this probability as the area in the following area of the following parallelogram, where the side is given by this GAI, the quality term, right? So bigger this vector, the better the quality. And of say, in this case, we're just considering say only two terms, and the angle between this vector is essentially your similarity score. Okay. So in this case, when your items become, so in this the first figure, as the quality increases, your area, right, your area of this parallelogram increases, which means the probability that you'll be selecting these two items together also increases. On the other hand, when the angle between these two increases, right, or the similarity score increases or the angle decreases, then the area under the parallelogram also decreases, which means the probability that you'll be selecting these two items together also goes down, right? So you can basically control this quality diversity trade-off using this quality diversity decomposition. Okay, so what we now really need is not a DPP, but we actually need a conditional version of DPP, right? So why do we need that? Let me explain that through an example from machine learning, because it is a pictorial sort of an example, so it will be easier for me to explain that way. So let's say you have a large image library, right? And the goal is to show some images from that library based on the input that is given to you from the user. Let's say the user input is New York, right? Then obviously the goal is to show some good images of New York. And this is where, first of all, the quality diversity trade-off comes into the picture. You need to show, right, good images, meaning high quality images. At the same time, you should not be showing images, all the images of the same place, right? So which means you need some diversity also in those images, and that is where the diversity part comes into the picture. Now, why is it a conditional DPP, right? You're not inducing a distribution on your image library, but it is a distribution that is conditional on the input being New York, right? So that is where the conditional DPP comes into the picture. So our input will be represented by this variable X, right? So all the probabilities will essentially become conditional on X. Okay, so that's pretty much what I wanted to convey here. Now, how does the learning part works, right? So what exactly are we trying to learn here? So we are going to set up a learning framework, which we are calling DPP learning framework or DPPL. So here we will have to come up with some models for a quality score and the similarity, right? So we are modeling the quality using a log linear model. So G of AI, right? As I said, it is conditioned sort of on the input. So that input will always remain. It is parameterized by these parameters theta. This could be of course, a vector as well. And then we have Sij, right, which is the similarity. We will be using a Gaussian kernel for that. Okay, so why did we choose these two specific things? Again, they are not really important. What is important is what exactly are the parameters, theta and sigma. You can read the paper for more details, but the reason is that under these assumptions, right, your log likelihood will become a concave function. So the learning process becomes easier. Okay, now the learning step, right, is to have some training set, right? So in this image search example, right, let's say you already have a really good recommender system. So you have an input and then you know which images were shown by that recommender, right, for X1 or image search system. And then you have XK, right, to YK. So you have these K samples in your training data set. Right now, you can train your model by writing the log likelihoods, and we will be going into log likelihoods on day 2 in a lot of detail. So I won't be going into these expressions now, but you can maximize the log likelihood to get the optimal values of theta and sigma, right? So again, more details are in the paper. So how exactly are we going to use this now, right? So we are going to, so this can be applied to many problems. This sort of general idea can be applied to many problems in wireless, but we are going to apply this to a simple link scheduling problem. So in this problem, we have M transmit receiver pairs. Okay, so these transmit receiver pairs are shown by these small sort of dumbbells. Let me go back here. Right, like this is one transmit receiver pair. We have M of these. You can think of these as think of this network as a bipartite graph, right? You have transmitters, you have receivers. Each transmitted is connected to one receiver, essentially. Right. Now the problem formulation. So what we are trying to do is we want to come up with power allocation for each transmitter. Either it will be a high power transmitter or a low power transmitter. High power transmitters will be transmitting at PH, and the low power transmitters will be transmitting at PL, right? So rate on the ith link will be given by log2 1 plus this term is nothing but SI and R, right? And SI and R is nothing but the received power on your own link divided by the noise power plus the total interference that your link is experiencing, right? Now, as some of you may have already recognized, right, this is a classical problem where we are, we set up some objective function which could, for example, be just maximizing the sum rate. Right. In this case, we can define the total sum rate of all the links. Right. So this is the sum rate subject to our power allocation restrictions. Right. So we are restricting the power to either PL or PH. This problem is notoriously hard. Right. It is an integer programming problem. But it can be solved iteratively by geometric programming for say small to moderate size networks. You even heuristics, right? You cannot really using heuristics, you can't really solve this problem for extremely large networks, right? Then the question is, can machine learning help? Okay. So we came up with this DPPL, and we applied this to the link scheduling problem in the following way. So we have a given network configuration, right? So this is, think of this as New York, right? This is what sort of we are conditioning on. Then for this network configuration, we are generating optimal schedule using a heuristic, using this optimization algorithm that I just showed before. So we are getting an optimal schedule, which is given by this epsilon star here, right? So for a given X, we know which of the nodes are so which of the nodes should be simultaneously transmitting, right? Or which of the nodes should be scheduled in a given time slot. And that information is contained in YI corresponding to XI. This creates your training data set. Okay. Now, using this data set, you train your DPP, right? So as we discussed before, so there will be quality diversity trade-off. So which means that we need to now decide what quality means in this case, what similarity means in this case, and so on. Now, this is really up to the designer to choose. And in this case, what we chose was, we defined the quality in terms of your own receive power, right? So high power or channel gain, I should say. Better channel gains means that link is of high quality. At the same time, we also don't want high interference, so we considered interference from the nearest two nodes. Okay, so similarity in this case is defined in terms of the distance. So if two nodes are located very close to each other, we say that those two nodes are similar, right? Because we don't want to select them to transmit on the same resources because they will interfere. Just one way of selecting quality and diversity. Under these assumptions, we trained the DPP. And once you have that trained model, which is nothing but this L matrix, okay, then you can use that model to actually directly sample. So for a new unknown network configuration, you just sample directly from using that DPP to get your estimated schedule. Okay, so that estimated schedule for the new sort of test data will be epsilon hat star. Right. So this is what the DPPL is, and let me show you some quick plots. Okay, so here we have the optimum plot, which is this orange plot here. Right? This is the optimal. Of course, whenever this is coming from a heuristic, so I shouldn't say optimal. This is suboptimal, but this is sort of surrogate of optimal in this plot. And then we have two plots corresponding to DPP. Right? The way we sample will dictate its performance. And then we have independent thinning. Okay, so this is the CDF of the sum rate that we are getting. Right, so let me talk about these two different sampling methods for the DPP. So when I say DPP sampling, that basically means one-shot sampling. We have a distribution, we just sample with that distribution. Now map inference, right, as we describe in the paper, basically means we are coming up with Y hat, which just maximizes the posterior. Okay, so this is your trained model, and then what is the posterior for that model, right? We're just trying to maximize. It turns out this is a hard problem. This is a NP hard problem, but there are some efficient solutions available in the literature that that were used directly to obtain this curve here, the dotted curve. Okay, but interestingly, the complexity of both the sampling, direct sampling and map inference methods pretty much is the same as we show here in this plot. And this complexity is many orders of magnitude smaller than the complexity of the heuristic that we used to generate the training data, right? And it turns out, if I remember correctly, you cannot you cannot apply that heuristic to large enough networks. So that was the problem we were facing when we generated this training data set. And I think we had to limit our training data set to about, on an average, around 20 nodes. And you notice here that if we apply whatever we have learned, even to a larger network, we are still getting some gains when we use map inference. Right? So notice this plot here, it is still going up. So we are still getting some gains. So which means that the pattern we have learned of the optimal schedule is applicable even for larger network sizes. All right. So I had one other case study. I think I'll just leave that for maybe a future lecture, just because we are nearly out of time. If I start that, I will need, yes, I think we'll just be over time after that. So let me actually summarize, because I think all the key ideas have already been conveyed in the lecture. So in this lecture, we discussed the role of machine learning in communications, or rather, I should say, we have started discussing, right? This is the first of a series of lectures on this topic. So today's case study was focused on using machine learning for approximating algorithms, right? So I showed one case where even a heuristic won't give you a solution, but then if you train a machine learning model using, we used some ideas from stochastic geometry in conjunction, you can at least get reasonable results. Okay. And this idea, by the way, of subset selection, it is not really limited only to link scheduling, right? So there are many different types of subset selection problems which occur in wireless networks, and they can all benefit from this type of thinking, where you try to learn what your optimal algorithm is doing, then you come up with some probabilistic learning method to approximate that behavior, right? That's really what we did. So, all right, I think I'll just stop here, conclude this lecture, and I will see you guys in the next lecture. Thank you so much for your attention.